Hello everyone, this is MsDeep 𝐒𝐲𝐬𝐿 and I'm back with another discussion where we will be talking about chapter 11, summary of designing data intensive applications book. Okay, so till now we have covered till chapter 10. Today is the chapter 11, which is stream processing. We will be discussing what's in the chapter and basically summary of it. If you want to read it entirely, I will be sharing the link with you. The book can be read online. It is available from the 𝐒𝐲𝐬 website, so you can download it from there and you can read it from. You can also order an offline copy from Amazon. I will be sharing that link with you as well. So let's get started. Okay, so the last chapter in which we discussed around batch processing, right? The main difference between batch processing and stream processing is that in case of batch processing, the input data is kind of fixed. Okay, you know that this is my input and I have to do some kind of processing and then I will produce a output on the top of this or on top of this data. Okay, but in contrast to the batch processing logic, like whatever we did there, in case of stream processing, data is made available incrementally over time. Okay, so there is no fixed data set. Okay, if you see the batch processing system, the input is bounded. Okay, it is not changing. But in case of stream processing or like stream databases or whatever related to stream, the data is unbounded. Okay, the data is unbounded. It means that data keeps on coming. You don't have a fixed set of data which you can say that okay, I have this amount of data and I have to process it. You are not saying that in case of stream related systems. Okay, because data keeps on arriving. So this is the main difference between batch processing and stream processing. Great. Now transmitting event stream, how does it work? Okay, so what is your input? In case of your batch processing, we discussed that input is your set of some files which are stored on HDFS and then you are trying to process it via MapReduce or Spark or Flink or any of the frameworks which are available. Okay, in case of stream processing, you have a set of input. Okay, when I say input, it is some sort of events that keep on coming. Okay, so what is the input? Sequence of records or event. Okay, there is some event which is happening, they keep on coming and your system keep on processing them. Event is an immutable object. Okay, it doesn't keep on changing, so you receive one event and it is immutable. Okay, then you will receive a new event. Okay, it's not that your existing event is updated and then you send it. There is no such thing exist. Okay, once the event is created, it is immutable, it is not changing over time. Whenever there is a new update, you will be sent with a new update or new event. Okay, so event is an immutable object containing details of something happened at some time. Okay, let's say order is placed on e-commerce website. So whenever you place an order, event is generated. On that event, other actions can be taken. Okay, let's say once the order is placed, I have to start with the shipping you have to start with the fulfillment cycle of that order. Okay, so that can take place based on receiving that order event. Event is generated by one producer, which is also called publisher, and it can be processed by multiple consumers or subscribers. Okay, so the basically stream processing operates on the principle of consumers and producers. Okay, producer is producing some events and then consumer is consuming those events. Okay, this is the basic principle and it is also called as publisher subscriber model. Okay, we will be discussing that again how it works, but yeah, this is the general idea of it. Related events are grouped together into a topic or stream. Okay, so let's say you have order topic or order stream. Now all the order events are published on this topic. Okay, none of the like payment related events will be published on this topic or stream. Okay, so you are trying to group together so that the subscribers who are interested in order events, they can subscribe to that particular. If something some system is interested in payment events, that system will be subscribing to those topics, payment related topics. So that's the idea. Related events are grouped together into a topic or stream. Great. Now messaging systems. Okay, as I mentioned, we have something called as producer, something called as consumer. Similarly, you have something called as publisher or subscriber. So your messaging system generally operates on publish subscribe model. Okay, producer is publishing and consumers are subscribing for that particular data and then they are consuming. Okay, whenever a new update is coming, multiple producer nodes can send messages to a topic. Okay, so you have some sort of topic here. Okay, you have producers. These producers are publishing the data and there are multiple consumers. These consumers are consuming the data from here of this topic. Great. Now what happens if producers send messages faster than consumers can receive them, not send them, receive them? Okay, so what happens? if let's say there is a producer and there is a consumer, and this producer is sending the data at very high speed, okay, there is very high speed, but consumer is only receiving at this particular speed. So there is a difference, there is a gap, okay, there is a gap in the speed on which the both the systems are working. So there are three potential solutions here. Either you drop messages, okay, the consumer can drop messages. It like, let's say it is producing 4 messages and the subscriber is only consuming 3, then either it drops the messages, that's one approach. It can buffer the messages, buffer as in it puts in some queue that, okay, keep the messages coming, I will process them whenever I have my threads available, or like worker threads available, so that they are stored temporarily in some data store. Apply back pressure. Back pressure basically means you are saying to that sender, then don't send me more messages. Okay, right now my my processing power is full. I can't process any more messages, so hold for a while. Okay, so this is what we call back pressure, blocking sender from sending more messages. So you are saying to sender that bhai इतना ही एक बार इतना ही, ठीक है. So once that processing is done, then you can ask again for producers to send me more messages, and then I will continue on processing. Okay, so this is the general idea. These are the 3 things which can be done if producer is sending more messages as compared to the rate compared to the consumers receiving them. Okay, that's the general idea. Direct messaging from producers to consumers. So there are 3 ways how you deliver those messages. One is without any intermediary nodes. So there is a producer, there is a consumer, you can directly sending the messages to those producers. Another way is UDP multicast in financial industry. So there is a stock broker system, not broker, a stock exchange system. That exchange system is basically publishing the message, publishing the data via UDP multicast to all the subscribers who are interested in those events. Another thing is webhooks. You might have seen this generally, like I have discussed this in a couple of payment videos. Webhook basically means like you have your system, and this system basically exposes some kind of endpoint. Okay, so let's say you have this your payment system, pay system. Okay, this is connected to API gateway, and it has some endpoint. And this is your let's say Razorpay. So you earlier you sent a payment request, you received the acknowledgement. So generally the payments work in async fashion. Okay, you receive the payment update once the request is sent by the payment system. Okay, because the Razorpay also has to talk to other banking providers, basically banking entities. Okay, so that can take time. So the acknowledgement ID is sent. Once the payment is processed, okay, or like whenever there is any new update, failed, success, anything, that update is sent to this endpoint. Okay, so this is what we call it as webhooks. Consumers expose the endpoint, and producers can push messages directly to this endpoint, and from this API gateway or like whatever endpoint you have exposed, this system can consume these messages and then act upon them. So what are the issues? Assumption producers and consumers are online, or application logic should be aware to handle fault. Now the idea here is, like in all these approaches, the idea here is that both producer and consumer are online. Okay, when I say online, there is no one in between who can handle scenarios if there are any faults. Okay, let's say my producer is offline. Now in that scenario, that message will be basically lost. Okay, you will miss the message. Consumer is offline, like let's say this sent the message, but this was not available to receive the message. So what you will do? You can't do anything. That message will be lost. Okay, so that's where the message broker comes in picture. Message broker or message queue. How they help is they act as a temporary storage. So the message broker runs as our producers and consumers connect as a client. So this is your message broker. It is a intermediary entity, and here is your producer, and here is your consumer. Okay, so these producers and consumers both connect to this. Producers connect to message broker to publish the messages, and these consumers connect to message broker to receive the messages. Okay, so they subscribe to the message broker so that they can receive any new event received or like published on that particular topic to which they are subscribed to. Okay, so producers write message to broker and consumers read from the broker. Durability is handled by the broker. Durability basically means the data is not lost. in case of any faults or any other scenarios like that. Okay, so that's the general idea. Now let's compare this message broker with a database. How, like, what's the general idea behind message broker? We say that you are storing those messages. Okay, you are storing the message to handle faults and offer durability. Now if you compare them with the databases, where they stand. So databases keep data until deleted, explicitly deleted. So whenever you send a delete request that delete this data from this table or remove this entire table, then only the data is removed. But in case of message broker, the data is deleted on various factors. One factor could be that delete them after, let's say, 14 days. Okay, that's one idea of it. Another could be that delete the message once it is consumed by all the subscribers. Okay, if it is consumed by all the subscribers, I don't need that message anymore. So in that scenario, you can remove it. Okay. Another thing is, the databases also provide multiple search capabilities. When I say search capability, basically you can create indexes, you can search on the primary key and all those things. Those things are not available basically on the message broker. So don't treat message broker as that kind of database storage. You understand, or like you use message broker as a temporary storage, transient storage, where events are kept until and unless the data is delivered to the consumers. Okay, that's the general idea of it. Let's discuss around multiple consumers. So multiple consumers can read from message from the same topic. Okay, so first thing is load balancing. Each message delivered to one of the consumers, so consumers can share the work. Okay, now the idea here is, let's say if for a single system you have multiple consumer nodes. Okay, this is your single system, you have 5 consumer nodes. Okay, and these all are consuming the messages from this message broker, from this topic. So if this is consumed from this, then they don't have to consume that same message. Okay, so you have some sort of load balancing which can handle this behavior. Fan out each message delivered to all consumers. Okay, this is one of the scenario that you deliver each message to all the consumers which are there, and then consumers handle it on basis of some application logic or however what they want to do it. That if it is let's say processed by one, or if it's already processed, then you don't process it again. These two patterns can be combined as well. Yeah, they can be. So again, like as you look at different message brokers which are available, like Kafka works on some different logic, SQS works on some different logic, RabbitMQ works on some other logic. So there are a lot of message broker services available, both open source and offered by cloud providers. So you choose depending on whatever your requirements you have. Acknowledgement and redelivery. Okay, there is a scenario that the message was not delivered. Okay, to the consumers, or you don't know if it was delivered. Maybe it was delivered, but you don't know as a message broker. So what you can do, you try to do some sort of redelivery. Okay, so acknowledgement and redelivery. So let's say the consumer crashed, messages were delivered by consumer but never processed by it. Okay, that's one idea. Not one idea, that's one of the potential problem that could arise, that consumer is processing the message, but it was never able to process it because it crashed in between. Okay, consumer should send so to handle this behavior, what you can do, you can ask consumer that whenever you receive the message, okay, let's say this is your, let's clear the space up. So the idea here is that you have your consumer, and this consumer, what it does, this is your message broker MB, and this is your consumer. Okay, so this message consumer, either this is sent by this one, or like consumer consumes, whatever the arrow direction is. So let's say once this is consumed, the consumer will send acknowledgement message that for this message ID 1, I have consumed this message successfully. Now you can delete it. From my end, I don't need it anymore. Okay, so that's the one idea. Consumer can send acknowledgement message that the message is consumed. If a broker is unsure of message delivery, it can always be retried. Okay, then it falls on the consumer end that there are some scenarios where the message may be delivered twice, so your application should be able to handle that. If message ordering is important, okay, if let's say you want to say that now let's take an example of that order processing event. Okay, so whenever the order is placed, okay, so first the order is placed. Okay, once the order is placed, then you confirm the order. Okay, so this sequence of events should be in the same order. Okay, so that the logic or the consumer system knows that okay, the order is confirmed, now the payment is done, so the application confirmed the order. Okay, so if they are not received in the same sequence, your application system should be able to handle out of order events as well if they happen. But let's say if the logic is important and you want to handle that at a message broker end, what you can do, messages can be, okay, recommendation is to keep separate consumer per queue. there is another one more logic which will be discussed in the case of partitioning. Okay, the idea here is that if that ordering is important, you publish or publish all the messages to a single partition. If the, let's say, message broker is running on multiple nodes, so you publish those messages on a single partition, so it handles that order of those messages, and then delivery can be handled in the same fashion. Partition logs. Message brokers are built around transient messaging mindset we discussed, and then we also try to compare it with the databases. Okay, so they are built with a transient messaging mindset. Delete after delivered. We are deleting those messages after they are delivered to the consumers. Databases files we already discussed, they are only deleted on the user request. So if messages are delivered, they can't be recovered. Okay, so this is the general philosophy followed in this AQMP or JMS style messaging systems. Okay, now can we have durable storage plus message notification? So you want this AQMP JMS style messaging, plus you also want to have some kind of durability. Okay, so instead of deleting or removing the message once they are delivered, what you want to do, you still want to keep the messages, let's say for some time, let's say 14 days. There is always the time which you can configure. For Amazon SQL it's 14 days. For Kafka I think it's configurable, and then you can also ensure that whenever until your disk is not full, you can keep the messages. Okay, so the other idea is how you can use logs for message storage. Log as in append only files. Okay, whenever you see log basically means you are appending the data and you are not updating the entries, immutable kind of thing. Okay, so log is your append only sequence of records on a disk. This approach is used to implement message broker. This is same used by Kafka. Producers send messages by appending to the end of the log. Consumer received by reading the log sequentially. Okay, and it is much similar to Unix tool command tail-f. If you have used it for debugging the logs, so I have personally used tail-f heavily for debugging, live debugging any of the applications. Okay, so it is much similar to tail-f, like the consumers are receiving the messages, so they have subscribed this tail-f. So whenever a new update is coming in the log, they are consuming that. Okay, and for more scale, the log can be partitioned across multiple machines. Okay, it is rightly possible that you are not able to handle that all the logic on the same machine. So it is those message broker is deployed on multiple machines, and they are divided by the partition. So topic can be defined as a group of partitions to carry a message of same type as well. Now each partition broker assigns monotonically increasing number, okay, which is called offset. Okay, and both consumer and producers work on this, that till this offset I have these messages delivered, or from consumer standpoint it can say that till this offset I have read the messages. Now if I have to start again, I will start from this particular offset. Okay, so that's the general idea. No ordering guarantee across different partitions. So if you want ordering guarantees, they are only provided within a single partition. So all messages that need to be ordered consistently route them to the single partition. Okay, that's the idea of it. Example, Kafka, Amazon Kinesis streams. Okay, and same principle works for Amazon SQL FIFO. Okay, now logs compared to traditional messaging. In general, message broker can assign entire partition nodes in a consumer group. Consumer reads messages in partition sequentially in a single threaded manner. Okay, so you are publishing those, like producer is publishing those messages on the partition, and then consumers are subscribed to them and they are reading one by one, like these are my messages and I have to process them. What are the downsides? So the number of nodes sharing the work can be almost the number of log partitions in the topic. Okay, so because it is done in a single threaded fashion, there is no multi-threading involved, so the maximum number of nodes which can be involved here would be that number of partitions which you have. Okay, and if a single message is slow to process, it can also block others. Okay, since you are doing one by one, let's say M1, M2, M3. Now this M2 took so much of time, so this M3, M4 will be blocked till this M2 processing is completed. Okay, and if let's say these downsides overweigh or pros of log based messaging, then you can use JMS and AQMP, which we discussed shortly earlier. Great. Consumer offsets, the monotonically increasing number. So all message brokers with offset less than consumer current offsets has been processed. So we can say that whatever offset is currently, like let's say my offset is 5, so offset from 1 to 4 are already done, already processed. Okay, broker doesn't need acknowledgement every message. Why? Because it can take snapshots in between that till what offset the data is consumed by the consumer. Okay, just periodically record the consumer offsets. This helps in increasing throughput as well, because you don't have to wait for acknowledgement again. So there is no the dependency is removed from every message to periodically taking the snapshot. Disk space uses. Now if you are keep appending to the log, it will run out of disk space. So what you can do, there are two ideas: either you delete it, either you archive it. So those are the two ideas. Okay, so you delete the you divide, not delete, divide the log into segments, and then you can keep on deleting the old segments, or you can move them to archival store. So the next topic is databases and streams. Databases and streams. Okay, so the event can also be any operation on the databases. Writing to a database, this event can be captured, stored, and processed. Replication log is stream of data events produced by the leader. Okay, so the general idea is like whatever is happening in the database, this is your database. Now whatever is happening in the database, let's say I added a new entry M1. Okay, I removed this entry M1. Okay, so whatever operation is happening, you can also treat them as events, because something is happening on that database. You will be the direction I'm going is the CDCing and event sourcing. So we will discuss that shortly. But the idea is like whatever is happening in the database, whatever the happening is in primary database, you are trying to convert those into events, and then you are publishing. So if the system is responsible that what is happening in the primary database, I want to know. Okay, so they can capture those as events. Okay, so producer is your database, and then your consumers are other systems, other subsystems, other stores which are interested in this data. Okay, keeping systems in sync. So same data can be stored at multiple places in different forms for different use cases. One of the idea is that the payment system we discussed, right? So for payment system, you have your main primary, let's say Postgres database. Okay, so now whatever happening is this Postgres database, you are also publishing that data so that it is consumed by your analytics database, and you can then run all sort of aggregations on top of that data. Okay, or let's say for order event or inventory kind of thing. Okay, so you have your primary database, let's say DynamoDB, in which you are keeping all this data, but you also want to offer the search functionality on top of it. So this same data is consumed by Elasticsearch or open source cluster, where this data is indexed as per what kind of search criteria you have. So you have all those keywords filtered out. Okay, so you can offer that search capability based on that like from that data source. Okay, so these are few of the examples where it is used. How can you do it? So, okay, so one thing is full database dumps. So whatever data you have in your database, you dump that database data into the another data store. Okay, that's one idea. Another is dual writes. Dual writes means you write to the main database, you also write to the another database. Okay, so application is responsible to write to multiple data sources. There can concurrency issues can happen. Okay, because you are trying to write to two multiple places. It can also happen that write can fail on one place and it succeeded on another, so you have to handle those kind of rollback kind of mechanism. So you need transaction support across the multiple databases, which is hard to gain. So the idea here is there are two ways, easy ways through which you can implement this. One is CDC, change data capture. So I created a dedicated video on my channel which is included in the systems and playlist. So go check out that. We have discussed what CDC is, what are the types of CDC, examples of CDC, how it is implemented. So all those details are covered in that video. But the idea is like whatever is happening in the database, you have your database log. Okay, append on the file, and from that there is some connector or like anything which can publish those events to a message broker basically. So you have your, let's say, Postgres database, and this is your bin log. For MySQL, I think it's bin log. Okay, and then from bin log you have your Debezium connector. This connector reads this and then publishes those publishes those events to Kafka. So this is connected to Kafka, and from Kafka, let's say you have your open source cluster, or let's say you have your Redshift cluster where you do the analytics per se. Okay, so this is the general idea of CDC. Log compaction. Compaction basically means you are shortening or compressing sort of thing. Okay, so let's say the broker only keeps the data for last 14 days. So if a new data source is added built on top of primary database, we need to build a new data source on top of the some snapshot. Okay, so the idea here is idea here is, let's say you have that log. Okay, when I say log, bin log basically. Okay, so what you have to do, if you want to ensure, okay, think it of in this way. So how will CDC work? CDC will work like whatever real events are happening at this moment. Okay, but let's say the database is already in place for last 1 year. Now I want to reconstruct a new data source. So from there are two options. Either you read the entire log, okay, that's one option. Second option is you read the snapshot. Okay, snapshots offer you some sort of compaction, because in case of that CDC, you have to read each and every event. Okay, so let's say there was one row M1 in your database. Now this event M1 was, let's say, created, then updated, then updated, then updated, then updated, and then there are, like, let's say 5 operation total. Okay, 5 operation. So if you are reading the log, you have to read these 5 operations and you have to process these 5 operations. But if you are reading the snapshot, you have the latest data in place. So you only have to read once and you have the data whatever is needed in the secondary database. Okay, so that's the idea of log compaction. Storage engine periodically looks for log records with same key, removes duplicates, and keep the most update of the key. For CDC system, if every change as a primary key and every new update replaces previous value of key, then it's sufficient to keep the most recent, right? That's what I discussed. So you can rebuild the new data source by reading log compacted topic from offset 0 without taking snapshot. So snapshot was one idea which I described just now. When I say log compaction, it basically means that you do not keep all the log entries if there were some duplicates. Okay, there were multiple updates which were applied on the same key, so you only keep the most recent entry. So instead of 5 entries on this M1, you have the latest entry in the log, which is achieved by log compaction, so that your search system, or like whatever secondary store you have, it is reading the data only once. I hope it makes it clear. Event sourcing, this is another way. CDC was one of the way. Event sourcing basically operates on immutable sort of stuff. So when I say immutable, you have all the events and then you are not updating them. So store all changes to application stage as a log of change events similar to CDC, but the idea here is applied a different level of abstraction. CDC database is used in a mutable way. Okay, whatever the happening is on the database. Okay, so databases don't have to be aware about CDC. It is an independent operation. We discussed some time back that this is your like 𝐷𝐵𝐺𝐸M connector here, right? Now this 𝐷𝐵𝐺𝐸M connector can work independently and it can publish the messages to Kafka. This database don't have to worry about like what this 𝐷𝐵𝐺𝐸M is doing until and unless it is not modifying anything in the log. Okay, so that's the only worry of it. So databases don't have to aware about CDC. It can an independent operation that can go on. Event sourcing, in case of event sourcing, application logic is built on basis of immutable events. Okay, so event stories append only. Whatever data you are keeping, it is append only, and updates delete are discouraged or prohibited. Okay, so it's some sort of ledger. Okay, so you can see event sourcing as a ledger. Ledger basically means you are not deleting anything. Think of it as, when I say ledger, it basically means, let's say you have list of credit and debit events. Now whenever you are crediting anything, you're not keeping the latest, like what is my current balance. Okay, you have list of credit and debit events, and then you compute all those events, and then you have final, like what is my current balance in my bank account. Okay, so, and that's the challenge. You have to derive the current state from the event log. You have list of events, and from those list of events you have to calculate the current state. What is my current balance basically? Okay, if a customer asks, you can't provide those list of debit and credit events. Okay, if customer asks for balance, you don't give him bank statement basically. Okay, so that's the general idea of it. So in case of CDC, the entry in database represents the current state. Okay, but in case of event sourcing, you need to look at all the event history associated with the specific entry and then compute the current state. You have to compute on every query. This can be done based on some application logic. Okay, we can do it. Recomputation again and again can take time. This is the issue. This is a downside for event sourcing. So what you can do, you can take a snapshot or cache in somehow so that you have a faster response time. So like you can, instead of computing them again and again, you can also keep them in cache, or you do some sort of snapshotting. Okay, any logic you apply is what you just want to ensure that the data can be served in near real time or in a faster way. Okay, example we already discussed, a series of credit and debit events so that you can reflect the balance to the customer. What are the issues? If there are more updates Computing current state is a challenging task. Okay, if there are a lot of updates happening on the same row, then it's a challenging task to compute the balance or the current state. Sometimes data deletion is a requirement, so immutably don't serve the process. There can be possibility, let's say deletion of or data for GDPR compliance. Okay, so you can't say that I will not delete the data. Okay, you can't say that I am using event sourcing, because none of that makes sense. If deletion is the requirement, then you have to delete it. That's the idea of it. Okay, so this can be one of the challenge. Okay, let's discuss the next topic, commands and events. So whenever a request arrives, it is basically a command, okay, that do this. Okay, once the system agrees or like some sort of validation is done, okay, I am performing this command. Once the command is written or like the processing is done, it is treated as an event. Okay, so you have your request arrived that pay money. Your system pay system validated that the system has money available. Okay, once the money is available, it sent the money to this particular C1 account to C2 account. Okay, so once this processing is done, then you generate an event. So this is the command, pay money from C1 to C2. And once this processing is done, once this money transfer is handled from C1 to C2, it is called as event. Okay. Another example is booking a ticket. Booking a ticket is command, check if seat is available. This is some sort of validation. Once the booking is done, then you generate an event which can further trigger, such as invoicing, generate events that invoice that booking is completed. Okay, till now we discussed like how you will process those, like not process, till now we have discussed that how will you consume the event, like how you will publish those events, and then how will you consume that events. Once the consumption is done, we are discussing processing of the streams. So process the stream once you receive it. You can write it to database, cache, search index, etc. You can push events to users, that is push notifications. You can also process one or more input streams to produce one or more output streams. They are called derived streams. Okay, so and the program handling this transformation from input to output stream is called as operator or job. Okay, so as part of processing, you can do all these sort of operation. You can write it to database, like you are writing it, you are doing some kind of, let's say you received a booking event, so you publishing a push notification that your booking is completed, or you generate some other events from this using this input. Let's discuss complex event processing. It is short for CEP. Okay, it is longer form of shorter form CEP, complex event processing. Now describe a pattern of events that should be detected based on some regex or filtering logic. So the idea here is that whenever you receive an event, okay, whenever you receive an event, if that event matches particular criteria or some regex or some let's say this key is matching to my request. Okay, if that match happens, then you generate an event. Okay, that event is called complex event with details of event patterns that was detected, that this particular key was requested which has to be matched. This is match, so I am good, and I am generating this SQL or the complex event. Okay, example SQL stream 𝐒𝐲𝐬𝐿. Stream analytics, you are doing aggregations over large number of events. So whatever events you are receiving, okay, whatever events you are receiving, you are doing the aggregations in near real time. Okay, now what example which we can discuss here is comparing current statistics to a previous time intervals. Okay, such as TPS or latency over 5 minutes intervals. Okay, so whatever events have received in these 5 minutes, you compare that latency to whatever was received in last 5 minutes, and then so on, so that you have those aggregations in real time. Some of the examples include Apache Storm, Spark Streaming, Flink, Kafka Streams. Okay, these are some of the examples. Maintaining materialized views, we also discuss some, like we discussed similar kind of flow in our last chapter as well, which was batch processing. What you are doing here is you are deriving the alternative view into the some data that you can query it efficiently. Okay, so you receive the streams, you receive those streams, you process it, and then you store it in some other database. Okay, or some derived data store. Okay, let's say search index built on top of database. So whatever update is happening in the database, you are also storing those updates in the search system, so that you can perform faster queries, efficient queries. Okay, reasoning about time. When I say reasoning about time, this basically means when this event was generated or when this event was consumed. So what kind of time or what particular time you are considering, what time you should consider for your system, that when this event was generated. So you can use time windows such as average over last 5 minutes. Now event time versus processing time. Okay, now processing messages may delay. Okay, there are some of the issues could be queuing. Okay, there are a lot of messages in the buffer and the consumer is not processing the messages as they arrive. It's not near real time, so there can be delay. And there could be network faults. Network issues happen because the systems are connected over the network. Performance issue in the message broker. Okay, message broker faced some issues, so it is not able to consume those messages. It didn't allow producers to consume those messages, and then it was not able to deliver those messages in time to the consumer. So it can confuse event time and processing time, and it can also lead to bad data. Okay, consumer wait time around for some time. Once it comes back, it processes the backlog of messages. Okay, so let's think that, let's say the consumer was down for some time. Okay, consumer was down for some time. Now it comes back online. Okay, once it comes back online, it will receive a bunch of messages. Okay, now let's say you consider event time, okay, event publish time versus the event process time. Okay, so if you consider the event processing time, you can say that there was spike in request. Okay, there was spike in request, but ideally, okay, in real scenario there was no spike. Okay, so if you consider the event time, there was no spike. The spike is observed because consumer was not able to process the messages for a short time. Okay, so if you consider this processing time, it could appear that there were no requests in this particular time, and then there were a bunch of requests in this. But if you consider the event time, then there were some requests in this and some requests in here. Okay, that's the general idea of it. So which clock you basically used. Okay, assigning timestamps to event is a difficult task if events are buffered at several points in system. Okay, it's a difficult task. I have created a dedicated playlist on this time. Okay, and what are the different clocks and all, so you can definitely explore that. There are really fascinating details in that playlist. I will share that link with you. So for capturing user events based on device clock, the user might deliberately set up a wrong time on device, so we can't trust it. Okay, so whenever, let's think of it, let's say whatever user activity is happening on the device. Okay, you have your application which is running on the device, so whatever activity is happening on the device, you use that device time to record that. But what if the device time is configured wrong? Okay, in that case you will not be able to capture the correct time. Okay, so the solution is you can use the server time when the event was received. Okay, but what if the server also receives the event after some time? Okay, it could be minutes, hours, delays. It could be due to bad internet connection at the user device. Okay, so that also can that also poses challenges. Okay, so that is also not a foolproof solution. So what's the solution of it? The solution is you log 3 timestamps. One is event occurring time as per the device clock. Okay, this is the one timestamp which you have to record. Event send time to the server as per device clock. Okay, this is the another thing. Second thing, third thing is event received by the server as per server clock. Okay, these are the 3 things you have to consider if you want to calculate the time accurately. And how you can use them, the offset will be, first to calculate offset, which is this third option -2. Okay, this is the offset to calculate. Once you do that, then the event occurrence time would be your time in the first event occurring time as per device clock plus whatever offset you have achieved. So this you can use as a correct time when this event actually occurred. Okay, let's quickly discuss type of windows. When I say type of windows, there are multiple types of this. I will quickly go through the definitions of them. So first one is the tumbling window. Tumbling basically means you have a fixed length of this window. Okay, and every event belongs to exactly one event. If you are publishing the events and then you are consuming those events from a particular stream, every event, whatever event you have, it will be part of that single window. Okay, in case of hopping window, it is also a fixed length, but it allows the windows to overlap in order to provide some smoothing. Okay, smoothing, not smoothing, smoothing. Okay, so that event can be part of not 2 windows actually, but the way you consider it. Okay, so let's say 5 to 510, and then this window will start from 508 to 520. Okay, so there is some sort of overlap. So this is what is hopping window. In case of sliding window, you contain all the records that occur within some interval of each other. In case of session window, there is no fixed duration. Session basically means that let's take an example that user was active. Okay, so let's say it could be for 5 minutes, it could be for 10 minutes, and if it's offline for some time, then you can consider that session as inactive. Okay, so that's the idea of session window. Stream joins. So let's say you have data present at multiple places, you want to create some derivation from that data, so we use joins. We discussed that same philosophy in case of batch processing as well. Here as well we are discussing the same. So there are multiple types of it. First is stream join, which is called window join. Okay, what you do is, let's take an example. You want to detect the recent trends in the search for URL. So whatever is being searched on your website, you want to do some sort of aggregation, or you want to do some kind of analysis. Okay, so system will store query and result return for each search request. So whatever the request is being searched in this search bar, you record that. Okay, once that is recorded, you also want to record whatever the search results will return. Okay, you search something, then there was search 1, search 2, search 3, search 4. Okay, so if these 4 search results will return, let's say user clicked on this one. Okay, user clicked on this one, so you also record this event. Okay, once that is done, the join would be you combine the click and the search query event for a key session ID in that particular session. Okay, if we quickly talk about implementation, stream processor maintains a state. Example, all events in last 1 hour indexed by session ID. For new search or click event, it is added to the index. Okay, stream process then checks other indexes for events with the same session ID to combine them. If there is some match happening, then system will emit an event saying that the search result was clicked. Okay, this is the one of the example how it is implemented. But the idea is there are 2 events happening, and then you are trying to combine them to generate some sort of analysis or some sort of another event to act upon it. Second type is stream table join, which is stream enrichment. Okay, you received some data and you are enriching it. We discussed the same example in batch processing as well, with the example of user profile data and user activity events. Okay, so you have your user activity events received. Okay, you are trying to enrich this user activity events from user profile database. Okay, so whatever event is occurring, what you can do, you can query the database that this user activity happened. Okay, what is the other details for this user ID? Let's say in the event I only received user ID. Now I also want to get the location of this user ID or the name of this MsDeep Singh. Once I receive this information from the remote database, then I combine this into the user activity event and then I use it. Okay, so you can query the database over network. This can be complex operation if you are doing it for each and every event. You can also try to cache this data in some form to avoid the network call. Okay, the database can keep on changing as stream is long running, so you can keep a local copy, but it has to be subscribed to the truth via CDC so that it can keep on updating. The last part is table join. Okay, table join, let's discuss with an example. It's easy to understand that way. So for let's say you want to build a Twitter's or X user's home timeline. Okay, so what you have to do is you have to iterate all over people who the user is following, then find the tweets and then merge them. Okay, it is an expensive operation. So what's the easy way out? The easy way out would be you build some sort of timeline. Okay, or like not timeline, you build a timeline cache based on some pipeline. Okay, the pipeline runs whenever a new user is publishing an event. We discussed this in designing social system. Okay, in our on our YouTube channel. Okay, and Instagram stories basically. So that design works on the similar fashion. What you are trying to do here is a user is publishing a new tweet, so it is added to the inbox of every user who is following you. Okay, so you are maintaining the inboxes for each and every user. If a new tweet comes in, you see that who this user is being followed by, and if there are list of users, then it is appended to all the users so that these tweets can be delivered to those users. Okay, for tweet deletion, you do same operation. Instead of adding, you remove them. Okay, let's say if a user starts following you too, if a new user following is detected, in that case what you do, you see what are the all the recent tweets of this user and then add to that particular user inbox. If it's an unfollow action, then you remove those entries basically. Okay, implementation. You have stream of events of these tweets, follow relationships, and you act upon them. Database with set of followers for each other. So basically you are joining the 2 tables, tweets and follows. Okay, so that's the idea of table and table join. let's discuss the final topic, which is fault tolerance. You have to somehow ensure the fault tolerance. Now in case of batch processing, what we discussed there was that if something fails, okay, what you can do, that job can be started again. Job can be started again because you have the input stored on the HDFS, and then you can process that again and then generate the output from it. In case of stream processes, how they generate the how they avoid the fault basically. So there are two ways: micro batching and checkpointing. Okay, in case of micro batching, what you try to do is you break the stream into small blocks. Okay, blocks are like miniature batch process, say over 1 second, and then you use that for processing. Okay, it is heavily used in it's a general concept being used in the Spark streaming, and it is called micro batching. You are batching the data over some time interval, generally 1 second. Okay, another approach is another approach is you are periodically generating rolling checkpoints of a state, okay, and then writing to a durable storage. Okay, so let's say for let's say every 10 events you create a checkpoint and then you write them to the database. Okay, so this is used in Apache Flink, and for any crashes, if there is some issues happening, then it can restart from the most recent checkpoint which was there. Okay, atomic commit. So outputs and side effects of processing an event affect if the processing is successful. So the idea here is that if the event has occurred, okay, so if the event has occurred, you have to ensure that if you are storing something, okay, if you were trying to take any action, it should only take action if you can say 100% that the processing is successful. Then only you are committing that data. Idempotency basically means you can perform that same operation again and again. So if you can process that event again and again, but the operation would be same. Okay, and this you can handle in your application logic. So if let's say the event has occurred multiple times, so if you can detect from your database that this event was already processed, so you ignore the operation altogether. So this is one of the way to handle idempotency. Okay, so this is all I want to discuss today in this video. This is the summary of chapter 11, which is stream processing, from the book Designing Data Intensive Application. If you like the video, consider subscribing to the channel. I'm MsDeep Singh. You will see the remaining chapter 12 as well in some time, and I keep on creating lot of these system architecture discussions videos on my channel, so you will learn a lot of things. Also, I'm author of a book, System Design on AWS, so consider checking it out. It is published by O'Reilly and with my co-author Jayant Kumar, so consider checking it out. You will learn a lot of things and how you actually design the systems, so consider checking it out. You can also explore it via O'Reilly Free Tier. Also, it is sponsored, 2 chapters are sponsored by Dragonfly, so you can check it out those. And then you can, if you see that, yeah, this is a real value to your knowledge base, then you can consider buying it. So we will meet again in our next video. Till then, stay safe. Tata. Bye bye.